All right, here we go with belt drives. So, not too crazy of a concept. I think it's important to understand that a circumference can be expressed as a straight line. At that point, we have two straight lines that we're comparing, in one sense, as far as the diameter. So we have the circumference, but the circumference is also relative to the diameter, or the radius, more to the radius than the diameter when we're talking about circles, hence the reason for radians. But anyway, so the diameter and the diameter. What we have here, you may recognize this. There's something very similar with what we've done in the past here. So the RPM times the driver, or the RPM, the driver RPM, times the driver diameter is equal to the RPM of the driven times the diameter of the driven. So here we have RPM being revolutions per minute. D is the diameter of the driver pulley, and lowercase d is the diameter of the driven pulley. So again, for these calculations, I'm going to keep the driver pulley on the left here, and the one on the right will always be driven. So if we take the driver with an 8 centimeter diameter, so right here, it has an 8 centimeter diameter, and then we have the driven pulley, has a 24 centimeter diameter, and none of this is to scale. So we got an 8 centimeter diameter, which isn't a whole lot, with 1200 RPM, and we have a 24 centimeter with 400 RPM. We want to calculate for, now all this is given already, let's say we want to calculate for the RPM of the driven pulley. So we just take the formula and right here, and we just plug all the numbers in. So we have, and again, it's all given, but just for the sake of calculating it, we just take all the numbers, plug them into the formula, assuming that this was missing, this was missing. So we have 1200 RPM times 8 centimeters, which is this right here, over 24. And again, the ratio of one to the other, and that gives us 400 RPM. If we keep going here to the next scenario, we'll just change a large diameter into a smaller one. So it stands to reason here, if you just think it through, that the lesser diameter is going to have many RPMs. This is not going to have so many revolutions, so you have 400 RPM. So if we take the driven, the D, RPM 1200, and the driver is 8 centimeters, or the driven pulley is 8 centimeters, what is the RPM? We just, again, plug all these numbers into the formula, mess around with the formula, and here we have, again, the ratio of these two diameters that's being applied to the RPMs. So you can express this similar to what we did with the levers, and we end up with 3600 RPM. So if we continue, give this a shot here. We want to know what the diameter of the driver pulley is. It has an RPM of 900. Our driven pulley is 6 centimeters with an RPM of 300. Pause the video, and we'll be back. And the answer here is 2 centimeters for the driver. So again, we're applying the ratio here, and we end up with 2 centimeters. And then, so we have the driver is 18 centimeters. We want to know the driven. So 18 centimeters, 840 RPM. Plug the numbers into the formula. RPM to RPM gives us 12 centimeters. So we move along now to some gas laws. We're dealing with Boyle's law. Now, the videos, I sent you the links, so as long as you've watched those videos already, this should not be anything strange. So just to recap here, we have ATM is an atmosphere, kPa, kilopascals, mmHg is millimeters of mercury. So we have P1, V1, P2, V2. So if we have P1 is 1.1 atmospheres, P2 is 0.76 atmospheres, V1 is 17 liters, and V2 is what? So we take those numbers. We have, in the history of ratios, we have the formula. But here we have P1 V1 equals P2 V2. So if we just rearrange everything, so you see here we're looking for V2. So we want to get V2 by itself. Well, just mess everything around here, invert. So we want to get V2 by itself, divided by P2, divided by, so we take on this side, divided by V2. And we end up with 24.6 liters. And again, recognize what's going on here. So if you take the same thing here, so we have atmospheres, kilopascals. We can express it a few different ways. So we have P1, 130. We want to solve for P2. Do the same kind of inverting. We end up with 5,200 kilopascals. So, if you want to pause the video and take a second, give me the answer. And here's the answer. So for Boyle's law, nothing too crazy. We have the ratio. Applying the ratio to the milliliters gives us 5.4. So, sort of more of the same. So here we have Charlet's law. And again, watch the video. There's nothing crazy, nothing too crazy here. A little bit of a different format, but we can rework it a little bit. We can make this V1T2 equals V2T1. And if this looks familiar to you, we should be good to go. So the only thing that you have to be aware of here is what's going on with the kelvins. 0 Kelvin equals minus 273.15. To be technical, I have this in the equations here, but so 273 degrees Celsius minus 273, negative 273 degrees Celsius, which is when they look at it scientifically, when everything stops moving. So in space, the temperature is just a couple degrees above 0 Kelvin. So if we take, so 10 Kelvin, 273 plus 10 gives us minus 263 degrees Celsius. We carry on down that line. So 100 Kelvin would be 100 minus 173 Celsius, 600 Kelvin. We go the other way. So because once you hit 0 Celsius is 273 Kelvin. So keep going, 600 gives us 327 degrees Celsius. So alternatively, 0 degrees Celsius is 273 Kelvin, since you've gone 273 degrees there. So 100 degrees Celsius would be 273 Kelvin plus 100 would give us 373 degrees. So all we do now is plug this all into the formula. So what we have to do though is convert from Celsius into Kelvin. So 35 Celsius gives us 308.15, and again I just a little more to the point here. Minus 8 gives us 265. And again, look what's going on here. The ratio of one to the other applied to the millimeters gives us 361.4. So, if you want to pause the video, we've got V1, T1, V2, we want to solve for T2, give you a second. And here we go. So we want to convert here. So 26 Celsius gives us 299.15 Kelvin. So we want to solve for T2. And what are we looking at here? The ratio of one to the other applied to the Kelvin gives us 209.7. So just to recap here, we have a few, what we've been working with is just to show once we get beyond all the wording in a question, you know, the jibber jabber, sometimes pawned off as critical thinking, and we deal simply with the numbers and with the formulas themselves. We've dealt with the torque equation, the diameter, and so here we have leverage, here we have pulleys, and we're dealing with gases here. But as far as the equations, this isn't quite the same, but it's important to understand the very simple math beyond the terminology and all sorts of things. Really just see these equations for what they are and the actual relationships here that we're just applying numbers to. It's very important to understand that mathematics is about relationships, and numbers are simply symbols. And if you can get beyond the words and things like that and just see the relationships within the question or whatever it is we're calculating for, you'll see that there's all sorts of similarities. It doesn't matter if it's leverage, pulleys, or gases. We have some similarities there. Some relationships are inverse relationships, some are proportional. But either way, if you just look at what's going on here, it's a little bit easier to see the similarities and how nature is functioning. So that's just a little for instance. So that is it for belt drives and gas laws.